We reduce and we reduce on both of these in order to get small versions of them. The first thing we do is this M stands for motion model. We run Lucas and Canati between those two, okay? And that gives us a flow field, okay? And what we do is we make, and that tells you how every pixel moves, we double up and multiply by 2 that flow field, and then we apply that to the next level down, and then there's this funny function called warp. We take that function, we warp the level 1 of t minus 1, and now that's almost the level 1 at time t. It's almost there. So you know what we can do because it's almost there? We can run Lucas and Canati again, right? We come up with a new motion field, add it back to the motion field that we had before, expand up, multiply by 2, apply and warp, and continue. And that's how the iterative Lucas and Canati algorithm works. I know that that's hard to see from a picture. Here is the algorithm written out as steps. So we're going to compute to level k, right? So we build all of our Gaussians up to level k. We initialize the flow field as being 0 at sort of k plus 1. Then what do we have to do? Well, you know, here we're doing it from level k to 0. So from the previous level, we have the flow field from the previous level, which of course is half the size. So we have to upsample the flow field. That's just expand it, make it twice as big, all right? And that's now the right size to map from level k to level k of t minus 1 to t. The problem is, if in the previous level something moved by 1.2 pixels, how far is it going to move now? 1.2 times 2, 2.4 pixels. So when I expand the flow field, which just makes it a bigger size, I also have to multiply it by 2. That's what the next step of the algorithm here says, multiply UIP and VIP by 2 to get the predicted flow. And then you warp that level of the Gaussian of image 2 towards image 1 in order to get 2 prime, or t minus 1 to t. Whether you call it 1 or 2 doesn't matter. And you just keep iterating, and then we apply Lucas and Canati again between the warped version and that same level of I1 to get this slight, what's called the correction flow. And we have to add that correction flow back to the expanded flow that we had before. That's what these equations here are doing. They're adding that slight difference that we now found back to the original predicted flow. Here are some results. So this is an example of the optic flow, and here's that tree. And you can see if we don't do it hierarchically, we just apply Lucas Canati, it does a nice job on the background, but up on the tree itself, where there was a large amount of motion, it gives you exactly what you'd expect, which is junk. But when we run it with the pyramids, we get a better solution. And so you get these nice, you know, flow fields here in the middle, also in the back. Now you'll notice we still have a problem at the boundaries, right? And why is that? Well, remember, at the boundaries, there are pixels appearing and disappearing. And there's no way that optic flow knows what to do when a pixel appears out of nowhere. Basically because you moved and now there are pixels that were invisible before are now visible. And so the optic flow along the occlusion boundaries is still a problem. And you need further processing to handle that. All right, so that's hierarchical Lucas and Canati. And as we described it, it gives you a dense flow field. It gives you a UV at every location. But remember, we said that we might only want to do Lucas and Canati at areas where the eigenvalues were well behaved. That is, the places that are kind of corner-like. So there's a version of Lucas and Canati called sparse Lucas and Canati, which is just that. It's a hierarchical version that's applied only to what they call good locations or good features to track. This actually comes out of some work by Shi and Tomasi and good features to track, and applying Lucas and Canati to it. And by the way, those of you who use OpenCV, the Lucas and Canati used to be dense, and then they just changed it. It's now actually sparse, so now it only gives it to you at a select set of points. And they sort of changed it without telling you, because the function still compiles, it just, your code just breaks a little. So, so you should only be using the sparse version. All right, so look, what I'm showing you here was sort of the state of the art of motion estimation 20 some odd years ago for derivatives. And for a first class where you're starting to do this, that's fine. We're not assuming you have any background in computer vision. But if you were to actually take a look at work that's going on now, you will find motion estimation that takes this as the basis and then it adds a lot of other stuff to it. So they worry about sort of how the gradient behaves, the constancy of the gradient. They have energy minimization terms. Remember we did energy minimization for stereo, and that came up to be a better solution. It not only had the local matches, but also had more global structure to it. It also does key point matching, which is saying I've got something that has moved a long distance. So remember, the short distance, the expansion works really well. We have to do things hierarchically to get the long distance. Or you could just use point to point, right? I know this point went over here. Let me fill in the stuff behind it or around it. And when you do that, you get sort of a much better result altogether. And this is an image taken from a paper that came out in 2009. That ends the lesson. I was about to say that ends the lesson on Lucas-Canati flow. That's pretty much true. It's only a little bit of a lie because we're going to see a little bit more of this derivative motion stuff in the next lesson. But basically what we did is we solved for a different flow at every point by assuming that a window over that point had a particular flow everywhere. And then we move the window a little bit, and now we pretend that in this new window the flow might be something different, even though those windows overlap, which is a little strange, but that's how you do it. So it's okay to have small errors along the way like that. But the idea, so there's a little bit of a contradiction here, right? In fact, that contradiction is in what I just said. We assume that a window is all moving the same way around a point, and we assign that value to that point. Then we move the window a little bit, and we throw away that last thing, and we say, we're going to assign it to the next point, even though those windows overlap. You might say, I want to carve the image up into sort of coherently moving patches. And so there's two parts of that. There's this notion of how do I do the carving up, and what do you mean by coherently moving? And what that means is you've got a model for the motion inside these regions. And the next lesson we'll talk about motion models and how we could find regions that behave according to some motion model. All right, welcome back to Computer Vision. What we're doing in this lesson is we're basically going to finish up motion estimation. And this is the raw estimation of motion with respect to sort of a motion field. Going forward, we're going to do things like tracking and other sorts of examples where we'll use motion in order to essentially process an entire video. But here we're only talking about frame-to-frame motion. In the previous couple of lessons, we talked about methods that gave us dense flow, except for that sparse LK thing, where we had a different estimate for each pixel. And we didn't have any real serious constraint between them other than something like local smoothness or something like that. That is, we were just imposing this on the image without any sort of real thought to what's going on within the picture. But suppose you know that the motion is actually constrained. Okay? So, for example, maybe you know you're just looking at something rotating and you want to recover the motion. All right, so that would put a constraint on the motion field. Or suppose you know that some object's variation in depth is small compared to the depth to the camera. Okay, so delta z is small compared to the total z. That gives you another constraint on how things move. In these cases, you might want to have sort of a model for the flow. That is, how do I think the points can be moving within a region? So here are some examples of models, and these are the same transformations that we talked about earlier when we were talking about doing mappings for homographies and panoramas and things like that. So we have very simple, so we basically go from the red to the green. So if we have a translation, right, so this thing just moved that way, and in a translation, how many unknowns are there?
2.
2, right. So since we get 2 equations for each point, we just need to track 1 point here, 1 point there. If I know that between them, I know how x changed, I know how y changed. 2 equations, 2 unknowns, great, everything's good. We have what's called a similarity transform. Similarity is where things can translate, rotate, and scale, all right? And that's 4 unknowns, 2 points, which if think about it, if I take a stick here, I can translate it, rotate it, and stretch it. I only need 2 points to know the translation, rotation, and stretch. Much more interesting is what's referred to as affine. I have this rectangle, and when I move it, I can translate, rotate, skew, all right? And so parallel lines remain parallel, and I have 6 unknowns, and we actually looked at the math before. One way to think about it is I take one triangle, and I map it to its corresponding triangle, and that's an affine transform. So there's 6 unknowns, and I can solve it with 3 points. And then finally, I know you're all waiting for this, right? Here it's written as perspective. We can also write this as homography. Now you're seeing why we don't have me writing anything. We did this before, right? We said if we have perspective projection of a plane to another plane, that transformation is a 4-point transformation, 8 unknowns. And that's because it takes 4 points, therefore, to recover homography. So each of these can be thought of as transformations or as motions within a region. So here's an interesting example. This is a great old slide. I think this slide is actually from the Psychology of Computer Vision book by Pat Winston, which I think was 1975. I don't know. It's just such a cool, because it was before we could do it. It's just beautiful. Anyway, so the idea is here is image on the left and another image on the right. And the question is, taking a time 1 and time 2, how are things moving? Well, if I just look at these 2 pictures, it's a little hard to tell. But if I give you the flow field, it's very clear what's going on, right? What's going on is the camera is moving forward, right? The camera is moving forward, which is inducing this flow field, all right? And that's the flow field of a plane. That's going to be a homography. And there is another flow field here, and you realize this thing called a daemon, and that's what's so cute, because back in the old days in AI, when you had little Lisp programs running in the background, and little things would run on their own and have their own behavior, they were called daemons. So this is a Lisp joke. Anyway, so you can see this daemon is actually just a planar cardboard thing that is moving sort of forward, and to your right, it's left. And you can see that from the flow field. And if you cut up this image into this area and then that area, you would have 2 different flow fields, both of which would be homographies. So they would both be modelable flow. All right? So I'm going to show you a couple different things. Some is more math, some is less math, but it's basically the mathematics behind modeled flow. You may remember from physics or somewhere else that if I've got some point that's at a vector r from the origin, let's say I'm the origin or the origin's in the middle of the object, doesn't matter. If that point is rotating about the origin with some angular rotation omega, and it's also translating with some translational velocity t, okay, the overall velocity of that point, I hope you remember this from physics, was v is equal to omega cross r plus t. It's just true. You can work it out. And here's what that looks like written out. You remember we did that crossing operator could be written as a matrix multiplication. We did that for essential and fundamental matrices. So that's all this is. We've just written out the cross operator as a matrix, where these are the components of rotational velocity, and these are the components of the translational velocity. In fact, that's what it says here. So Vx, V sub x, V sub y, V sub z are the velocity vectors in the world, in the xyz direction. Vtx, Vty, Vtz are the translational components in the world, and omega x, omega y, and omega z are the angular velocity components in the world. All right? In order to figure out how things are moving in the image, okay, this is how they're moving in the world. In order to figure out how they're moving in the image, we have to go from world coordinates to image coordinates. Okay. Here's our simple equation for, in a font that's too small to read, but it'll get bigger in a minute. It's okay. We're just going to use straight perspective projection. We're going to assume the origin is in the middle. We're going to assume nothing is skewed, etc. So the only thing is that we need to know the focal length, right? So little x is the focal length times big X over big Z. Same thing with y, right? That's our usual perspective transformation. Okay, that's x and y, but what about how x and y are changing given how the points are moving, given the v in the world? Well, it turns out that's pretty easy. We're going to call little u and little v here the velocity in x and the velocity in y. So these are just the derivatives in time. So this is how things are changed. So u is the velocity in x, dx dt, v is dy dt. All right? Well, so to take the derivative of x with respect to something, in this case time, right? How it's moving. Well, you remember the formula for the derivative